Welcome to the Liskov Substitution principle, the L in solid. This principle is all about inheritance done right. It tells us that any subclass should be able to stand in for its parent without breaking the program. Sounds simple, but violating it is one of the most common and subtle bugs in object-oriented code. Imagine you write a function that accepts a shape and calls its area method. You test it with rectangle, and everything works perfectly. Then a teammate adds a square subclass, and suddenly your function produces wrong results or throws an error without a single line of your code changing. That is the problem LSP addresses: inheritance that looks correct structurally but breaks behavioral contracts at runtime. Think of a rental car desk. The contract is simple. Any car we give you steers and accelerates the way you expect. If they hand you a car where the pedals do the opposite of what every driver expects, it does not matter that it is called a car. The behavioral contract is broken. LSP says your subclasses must honor the same contract your base type made with its callers. Barbara Liskov stated it formally: if S is a subtype of T, then objects of type T in a program may be replaced with objects of type S without altering any of the desirable properties of that program. Two concrete rules follow from this. First, do not strengthen preconditions. A subclass cannot demand more from the caller than the base class did. Second, do not weaken postconditions. A subclass cannot promise less than the base class guaranteed. Let us trace the violation first. Rectangle exposes set width and set height independently, and its contract implies they are independent. The function printArea sets width to 4 and height to 5 and expects an area of 20. Now we pass in a square. Because square overrides set width to also set the height, calling set height next sets both sides to 5, so area returns 25, not 20. The subclass silently broke the caller. The fix is to stop using inheritance here altogether. We define a shape interface with a single area method, then implement rect and square separately. Neither class can mutate the other's dimensions because they share no mutable state through a parent. Now print shape area works correctly with any shape. Substitutability is restored. It is crucial to understand that TypeScript's type system only checks structure whether the right methods exist. It cannot verify that a subclass behaves the way the base class promises. LSP is therefore a discipline you apply at design time. The key consequence is that when you follow LSP, polymorphism actually works. You can pass any subtype to any caller of the base type, and the program remains correct. When you violate it, you end up scattering instanceof checks through your codebase, which is a reliable sign something has gone wrong in the hierarchy. Reach for LSP discipline anytime you're building a hierarchy that callers will consume polymorphically, especially in a team setting where new subclasses will appear over time. A growing pile of instanceof checks is the clearest warning sign. On the flip side, do not contort your domain model to satisfy a hierarchy that should not exist in the first place. If you find yourself adding throw new error, not supported, to a subclass method, that is LSP telling you the inheritance relationship is wrong, not that you need a cleverer override. To recap, LSP says a subtype must be fully substitutable for its base type, not just structurally, but behaviorally. The square rectangle example shows how a geometrically intuitive hierarchy can silently violate caller expectations. The remedy is usually a shared interface rather than an inheritance chain. When you find yourself adding type checks or unsupported operation exceptions in subclasses, LSP is signaling that your hierarchy needs to be rethought.